Yep.
Yeah, very good. Yeah, a very good evening to all of you. In this particular session, we are going to discuss one week has been over with the crystallographic and the crystal symmetry and tensor course. Okay, so we are also going to discuss about that particular week only. But before we get started, let me introduce myself. My name is Vikas Kumar Mishra, and I am from the IIT Patna. I am doing my PhD under the Dr. Devendra Yadav. Okay. Uh, my research is mostly on the flash centering, which also involve a lot of the crystallography and all to understand the crystals. Like if you do PhD in any of the topic, in any of the metallurgical subject, subtopic of it, the crystallography is must. One should always understand that, and that's why this particular topic has excited me a lot. Okay, and in this particular lecture, in this particular courses, we are going to understand a detailed study of the crystallography, also the tensor and the symmetry related with that. Okay, so before we get started, let's get familiar with the particular portal or SWAM and how we can ask the question with each other and how we can discuss the answers and all. Okay, so let's go to the SWAM portal. You can just type the SWAM on the Google website, and there it will just ask for your Google link and all, and then we can start. Okay, so here we can see that there are the multiple options are available to us. Okay, here we can see the announcements will be there, and here is the about the course. Okay, you can see the entire layout of the course, like what are the things that we are going to discuss, and reference books and all. Okay, and yeah. Okay, you can also get the information that the how the assessment will be happening. Like 25% weightage has been given to the assignments, and the 75 will be based on the exam, which is going to conduct in the April. Okay. Next important thing is that you can click on this particular ask a question. Okay, so it will direct you to a page where you can ask few questions to us. Okay, since there is no question set, so it's not display any questions. Okay, so yeah, so you can always click on this particular click button, new conversation, and here we can your upload a question. Me or professor or any of the TA will try to answer it immediately as soon as possible to your questions. Along with that, the video recording of this particular live session is going to be recorded, and it will be posted on the YouTube link. Okay, and the link will be also provided to you by a mail. Okay, and so if anyone has missed this particular live session, let us say, still they can uh, still they can view the concept which we are going to discuss, the numerical, the questions which we are going to discuss. What are the what are the essence of this particular live sessions? Okay, that is something which we need to understand. The first thing is that so that this live session is conducted in such a manner that you are able to answer all the questions. That is most of the questions that is been asked to the assignments, week one assignments. Okay, let me show you the week one assignments that we are having. Let's go back. Yeah. So here we can see the week one. We can click on the week one, and here is a quiz one. Okay, and these are the questions. Just a minute. Okay. These are the list of the questions that you have to do and all. I'm just clicking on the randomly anything, and once you are done with your questions and answers, then you can directly go to the submit answers, and that assessment will be recorded by us. One more thing is that let us say you submitted this particular assignment once, and after later on you decided that no, some of the questions were wrong. You can improve further. So what you can do, you can again resubmit this particular assignments. Okay, so the final assignments will be considered for the grading and all. There is a due date also associated with this particular assignment, that is 7th of Feb. Okay, so make sure that you complete this particular assignment before it. Okay, so now let's get started with this particular. Yeah, so I was telling about that one part is that so that you are able to solve the numericals and the assignments part associated with this particular week. Along with that, if you have any doubt with the particular course in the topic which has been covered in this particular week, you can always ask me back. Okay, because the interaction with the recorded video is only a one-sided. Here we can do a two-sided interaction with each other. Okay, so feel free to ask any questions which has been covered in this particular week. Okay, we'll move systematically so that one student asked a week 5 question in the week 1. Okay, we will cover the week 1, all the possible questions of the week 1, and we will move forward. Okay, like if we are if we are in the week 5 live session. Okay, so one can always ask the week 1 questions. Okay, so that there is no confusion till the particular point. But we cannot jump to the future questions and we can ask that. Okay, it's so that it we can avoid ourselves by the getting confusions. Okay, so we'll move systematically. We'll discuss all the things that has been covered in the week 1. Okay, let us see what are the topics that has been covered in this particular week. These are the list of the topic that has been covered by our honorable professor Rajesh Prasad. Okay, so we in this week he has covered the what is the crystals, lattice and motive, lattice translation, unit cell, Voronoi cell, basis, and the crystallographic coordinate system. Okay, and he also discussed about the Miller indices of the direction. The Miller indices of the plane has not been discussed yet. It will be covered in the next topic, that is, sorry, next week, and that will be 2C. The video number will be 2C. So here we are going to discuss about the whatever has been covered from week 1 in week 1, that is 1A to 2B, and this is a final topic that has been covered in this particular week. Miller indices of the direction. Okay. Okay. So now let's move to the yeah. Before we move to the questions, let me ask you if you have any doubt from the conceptual point of view. If there's any doubt, yeah, please feel free to ask me.
Then please explain this Voronoi cell in little bit details.
Yeah, so we'll cover that particular part of the Voronoi cell. We'll solve few questions. You can also see that there is a one question on the Voronoi cell in this particular assignment. Okay, the last question. It is a very one of the very good questions. Okay, so I will not solve this particular question, but we'll solve few questions so that we are able to answer the this particular questions. Okay, we'll also understand what is a Voronoi cell and all. Okay, okay. Since there is no other doubt, we can move to the discussing the few questions. Let me make it a full screen. Pardon for me. Pardon me for that. Yeah. Okay. So here, this is one of the a beautiful pictures by the MC Escher. He's very famous artist in this particular type of drawings and all. Okay, you can always type on the Google MC Escher graphic art, and you will get multiple numbers of the arts of his. This is one of the art. Okay, so here we can see the multiple patterns that has been repeating, multiple features that has been repeating after a particular distance. Okay, so how about like the question is asking us that draw equivalent lattice point and a unit cell to the following 2D pattern. It is asking us to draw a unit cell and the lattice point. Lattice point, we know that what is a lattice point. It is a regular arrangement of the point in the space. Okay, pardon, it's not a regular. It's a periodic arrangement of the point in the space. So in crystallography, we always define lattice to be the periodic arrangement of the point in space. In two dimensions, it will be the space will be consisting of the two dimensions. So here can we see any lattice point? Let's try to mark. Let's select particular features. Let us say I am selecting this particular girl. Yeah, this girl particular. Let us select the chain of this particular as a lattice point. Okay, and so we can also select this particular chain to be a lattice point. Let's see whether yeah. So we can see that these are the features we can. So one thing is that once we are selecting the lattice point, we are selected this particular thing chain from to the next figure, we cannot select the head. We should always go with the same feature. Okay, make something fix it. If you are selecting the head, you can select you should select head in all the particular points in all the figures. Okay, so now these are the things which we are having. So the thing is that is this a lattice point? If I'm moving, let us say if I move by this particular distance, I'm getting the same particular symmetry, same particular features. Same with this particular lattice point also. If I'm moving in this particular direction, I'm getting the same feature. Okay. If I move this point to the diagonally, we'll get the same feature. And if I move this particular point diagonally, the figure is not like we can only show the part of the figure. The figure can go infinitely. So we will also see the feature associated with that. If you go some particular direction, in this particular direction, let us say, let me select a laser. Okay. Laser. So if we let us say if I go from this particular point to the head of this particular feature, okay, in this direction, okay, same. If I go in the same direction by the same amount, by the same magnitude, I will get again the same features. So let's see. Let's try to move the entire lattice and see whether this particular features is been repeat. Is there any other equivalent lattice point associated with this particular features? So here, let us say I selected this, and I am moving this entire thing to the chain of this particular. Okay, see, we can see that entire pattern has been again translationally equivalent. So this point can also be selected as a lattice point. Is there any other equivalent lattice point that we are having? Let us say, what about the head of this particular feature or chain of this particular feature? Again, we are having the same lattice point. We not change the magnitude and we not change the shape of this particular lattice. All we did, we just translated it. Okay. Again, we can select this particular feature, the neck of the particular girl, this uh, bottom oriented girl. Okay, vertically downward. Okay, we can see that again the same things is been repeating. Okay, so what we have understand from this particular question is that uh, multiple lattice point, equivalent lattice point can be associated with a given pattern. Okay, but what about the unit cell? Okay, can we draw the unit cell also to this? Unit cell is nothing but a representation, a small representation of a large, infinitely large feature, large pattern. So we can select this particular unit cell, and if I just repeat this particular entire part, entire this unit cell, translate it by a basis vector. Basis vector we have already discussed, I think, in the video. Yeah. Okay, so we can translate this in the vertical direction or the horizontal direction, and we will see that okay, yeah, we are able to form the lattice. We can generate the entire feature just by using this particular unit cell. Okay, if I translate it horizontally, this entire feature will be translated over here, and the pattern will be repeated, and so on and so forth. Infinitely, we can do that. Okay, so this was the first question, and we can also see that the same features is been there are one more features, one more drawing is been associated, but same MCS. Now for this, let us can anyone answer me that what are the is is this a lattice? Can this particular figure, this particular pattern, can it form a lattice?
Yeah, it can form.
How about the lattice point? If I selected one of the lattice point over here, let me take the laser. Let us say I'm selecting the tip of the face to be one of the lattice point. I'm associating here a lattice point.
Yep.
Same can be associated with here also,
Mm,
right?
yes.
Like this can be repeated. This entire features can be repeated, right? So what we
Yes.
can see is that let us say So if I'm having this particular thing over here, and the same point, one I can also see that there is one more point if I translate this by this particular distance, right? Same if I translate on the downward also, we can see that the same type of features are available, and associated with that we can associate our point to that particular tip of the fish. Okay, so now what we can see is that this thing this thing can be a unit cell. Not only this, like not only this particular point, can is there any other point which are equivalent to this particular lattice? Can we
Okay.
select any other point? Yeah, I think we can. Let's
Yes, we
see.
can.
And that will be what
What meant,
we can. How about this tail of this
yeah, yeah,
particular
this one. Yeah,
lizard?
same. I
Okay,
also think.
so I can select
If
this particular tail. Let us say,
yeah, this one, then here.
yeah, to the right we can go.
Yeah,
This one,
yeah,
and then where should we go? Up. Yeah, here we can also see,
yes.
and here.
And then, yeah, we can again
This
form.
entire thing, this entire thing will form a. This entire point can form a
Okay,
lattice.
let yeah,
Along with that, see, if I'm going any by any amount by in the same direction, let us say I'm moving to this particular from this particular point, the red one. Let us focus on. We select the red pen also. Yeah. So this particular red point, if I go by a distance in the same in this particular direction, let us say over here, and so here from here, if I go in the same direction by the same amount, I will get the again I will get the same positions. Okay. So all the features is in all the directions wherever I go, considering the lattice point, all the lattice points are translationally equivalent to each other. So this point, if I go by the same distance in the same direction with this particular one, we are getting the same feature, that is the tail of this particular lizard. Here also we are getting the tail of the lizard. Okay. How about this? Let us say we are starting from this particular tail of the lizard over here, and we are moving in the downward direction and going to the eye of this particular fish. Sim Considering the same thing, what we can do, we can select this particular tail of the lizard, and by the in the same direction, by the same magnitude we go, we can see that we can find the again the eyes of the fish. Okay, so we can see that the for a given features, for the given pattern, for the given net, there is a multiple lattice point, equivalent lattice point associated with them. Okay, so we will consider this particular points as a lattice point for a timing. But you also know that there are the multiple points or lattice points also available, which is equivalent to them. Okay. So now we can form this particular lattice. This is a unit cell. Okay. So if I repeat this particular unit cell, will I be able to produce the same? Will I be able to produce the features, entire features? So below this and below this particular line, the same features are available. If I cut this and paste it over on top of the above, we will get the same feature. Okay, so one can generate this entirely infinite pattern just by considering the unit cell. So unit cell, we can say that it is a representation of a particular lattice of a particular feature of a particular pattern. Okay, so I hope it's clear to all of us for now. Okay, so let's move to the next question. Yeah, so it's a basis vector. We need to discuss about the basis vector. So among the following basis vector, select the pair of the primitive basis. So can anyone tell me what is the primitive basis?
Basis only contains the means atom at its corner.
Yeah,
What is
but
yeah,
mathematically also we can write something for the primitive basis, right?
yeah,
Which we have learned.
that the translation vector having all the means the translation that is in integer. Actually, I didn't get the didn't pick up the right word, but
Yeah, yeah,
it is in integer. The vector.
yeah. So they said a and m and n. They belong to the, we can say this belong to the integer. That is -3, -2, -1, 0, 1, 2, 3. It can go in any direction.
Yeah,
Okay.
minus
Uh,
infinite to infinite.
yeah. The thing is that A and B, if we select, let us try to understand this entire thing from this particular feature. How about if I take this to one of my basis vector, and the translation should be in such a way that for primitive, if, for us to call it to be the primitive, the translation, this m and n should be such that if a and b, for particular, if a and b are primitive, okay, if they are primitive basis vector, what does it mean? That they will generate all the point, that is, they will generate all point of the lattice, of this particular lattice, by a integral combination of the m and n. So what we can see that the linear combination of a and b should generate all the lattice point. Okay, so we can see that a, if I move, if I just multiply, starting from this, let us say this is our 0, and if I'm moving in the a direction by the amount a, if I move from this particular point to this particular point, what does it mean? Here we can say that n is 0. Okay, m is 1. Now again we can move in the same direction. This is 2, and then m can be 3. Right? Starting from here, it can be 3. Now from here we can go in the b direction. What we can see in the b direction, we are going by the amount. So here n is 1. Okay. So similarly, we can see that all the things. Now, what, for example, let us say this is, I selected this to be the A. Instead of A, instead of getting confused, let us say this is a P and this is a Q. Okay. So if I am taking P vector and if I am taking the Q vector to be my basis vector, so what we can see, if I translate by linear combination, that is I multiply 1 with A for a time being. So what I will generate? I will generate the another alternate point. I'm not getting this particular point. I'm not getting this particular point. So what I'm able to do? All I'm able to do is I am able to generate the subset of the particular point, subset of the lattice point. Okay. So this particular type of basis vector, which only generate the subset, they are non-primitive. The primitive are those which are able to generate the all the point, all the lattice point. That is all lattice point. Right. So see, this is okay. So now let's go to our question. Our question was that, let's get back to our question. So now we need to answer that whether the following basis vector are the primitive basis vector or not. So let's try to draw the unit cell associated with that. Okay. What we can do, we can draw this particular order. We can draw a lattice just parallel to the b vector over here, and all we are doing, we are trying to make a unit cell out of the particular basis vector, from that particular basis vector. Okay, so we know that for the two dimension pair of vector is a the pair of the vector is a basis vector. For 3D we know that it is a triplet. We need at least three basis vector to define the 3D 3D lattice points. Okay, 3D lattice pattern or the net. Okay. So now we have selected this particular, we made this particular unit cell. What we can say about this particular unit cell, whether it's primitive or not, we can say that it's a primitive only because there is only one lattice point associated. Effectively, there are only one lattice point associated with this particular unit cell. and so we are calling this to be the primitive. What about this B, C, and D? Whether they are primitive or not? Can anyone answer? Whether C and D is a primitive or not?
Uh, C and
All
D.
we need to do is we need to draw a basis. We'll extend this particular. We'll, using this particular basis vector, we will draw a unit cell associated with them.
Yeah, it's a primitive only.
Yes. Effectively, it will produce only 1 point, so it is a primitive. What about this? Let's try to extend our lattice to one more point. Yeah. From this particular point, I am going in this particular direction. Let's go in this particular direction also. And same, we are making a unit cell. What about this? Whether it is primitive or not?
Yeah, it is primitive.
It's primitive. So what we can see that primitive, if our basis vector is forming the primitive unit cell, we can say that yeah, the basis vector are also a primitive in nature. So all the pair A, B, C, D, and E and F, they are primitive in nature. Let's select the another one more basis vector that we are selecting this. So what we can see over here.
If we actually, no, it is a non-primitive. mm,
Yeah.
This is vector.
Also, yeah, this is
Non-primitive.
non-primitive only, non-primitive. So here we can see that we are extending this and we are extending this. So this point is being missed. If I translate, if I use this particular basis vector that is, let us say, x and y, if I'm using this particular basis vector and I'm trying to translate them, so this particular point will be missed. So they will cover this particular point, then they will cover this point, but and again from here they will cover this point, but this point won't be covered. So more or less, that this part which we have discussed about the translation is equal to the m times a vector plus n times b vector. Okay, if a and b are able to generate all the points, if I am only having the one particular point over here, and I'm applying the a and b to the entire this particular point, like move this particular point over this particular direction, and then this particular point in this particular direction, and generate the entire. If it is able to generate all the lattice points, then we will call it to be the primitive. If it is not, if it is only able to generate the subset of the lattice point, then we will call it to be the non-primitive in nature. Okay, so I think this part is clear to us. Now let's go to the next particular type of questions. That is whether the following cell is a unit cell, whether this particular thing is a unit cell or not. And second, if it is unit cell, whether it's primitive or non-primitive in nature. Okay,
Okay.
these are the things which we need to discuss right now. Let's start with the A. Okay, let's let's discard the things. Yeah, so this particular PPT will also be shared to you on the by a link, and video, the link of the YouTube video will also be shared with you. So now, whether our question is that whether this is a unit cell or not. What is the
Yes, it is.
definition of
Yeah, it
it?
is
Is
a
the
unit. We can translate it and we can get the same, you know, we can generate this entire
entire
thing.
pattern? Yeah.
Yeah.
So the the basic of the unit cell is that what is like when we call the something to be the unit cell, if it is able to fill the space when we apply the translational periodicity to it
Yeah.
without leaving any gap, right?
Yes,
If it
yes.
is leaving any gap, then it won't be generating any. It won't be. We won't call it to be the unit cell.
Yeah.
So let's try to translate this in particular direction over here. Yeah, we are able to. It's not leaving any gap in between them. How about this? So this particular question, you remember that this is like our professor has left this question for us to solve. Okay. So here we can also see that yeah, it's not leaving any space. How about we go to the next part? Let's select two of them and try to translate them this time. Yeah, we are not able to any leave any gap in between them. Okay. And similarly, if you follow all the same entire thing, all the things, what we can do is we can say that yeah, we are able to translate them. Let's not select all them because we don't have much of the space. Okay, so let's try to translate this. Now we can say that yeah, we are able to fill the entire space without leaving any gap, and all we are doing is we are translating by the we are using the translation periodicity. Right.
Yeah.
The only thing that is we are using is translation periodicity. We are translating it by the translation vector. So see, we are not leaving any gap in between them, and we are also able to cover the entire thing, entire pattern. Okay, so we can say that yeah, this particular thing, the particular A is a unit cell. Now, since A is a unit cell, we got to know that now how to know whether it is a primitive or not.
Uh, we
How to know some
translate it by integer means uh, integer translation and see whether it is filling the gap or not, filling the space or not, and without
no
it means skipping any points in between.
whether it's primitive or it's not primitive. In both the cases, it will translate, and it will be it will translate, and it won't leave any gap in between them. Okay, so
Okay.
whether it's primitive or not in both the cases. Now our question is to answer that whether it is primitive or not. That can only be answered by the thing that if something, let us say, let me tell something. Is there pencil option is not there or what? Say, I think it's there should be something like draw pen. Yeah, here it is there. Yeah. If something is primitive, what does it mean? Entirely, it will contain only one lattice point. Okay. If it is non-primitive, it can contain more than one lattice point. Right? This is something which we know. In the first case of A, whether we how many lattice point does it associated with itself? Okay. So how about this? We can see there are the corner. There are the two types of atom two types of lattice point is we are having. One is this, the interior one, and there are the another type that is this one, exterior type. We can say A and B. Small V let's use. Okay. So now, how much effectively the point lattice point A is contributing to our lattice? It is nothing but 1/4. To this particular lattice point is contributing 1/4 to our lattice, to our unit cell. Okay. And how many of them are there? 1, 2, 3, 4, 5, 6, 7, 8. Will multiply.
Into it. Yeah.
And what about this B? How much does it contributing? It is contributing something like 3/4.
Three, yeah.
And how many of them?
Four.
There are four of them. So now we can cut them. We can cut this. This will be effectively we are getting, that is there are 2 plus 3. There is a 5 lattice point associated with this particular unit cell. So what we can say, this is not a primitive unit cell. We know that primitive unit cell only contain 1 point. Okay. Now, so is there any doubt associated with this particular like part A of the particular question?
No.
No? Yeah. Okay. So now let's move to the part B. Whether the part B, like we are able to answer the first question, that is whether this one, the part A is a primitive or not. Okay. Now we need to answer the whether this B is a primitive or not. Okay. Yeah. First of all, whether B is a unit cell or not, that is something which we need to answer.
Just
Yeah, it is a unit cell. If I repeat this particular thing, it will fill the
will
space,
generate the entire.
entire things. Yeah. Now the second question is that, so we can see that this is a lattice. We know. Second question is that whether it's primitive or it's not primitive. Okay. So now for that, we need to answer that how many points are associated with this particular unit cell. So what is the answer to that?
Hmm. So
Back to lattice point,
1/4.
it's one,
Yeah, one
right?
only.
This entire cell, we are seeing only one lattice
Hmm.
point
Yeah,
associated with it,
yeah. So it's
and this is,
primitive.
yeah, it's a primitive only.
Yeah,
So, like most people are confused that the lattice point should only be at the edge,
yeah,
and then only they will call it to be the primitive. No,
yeah.
it's not like that.
Hmm.
Here we can see that this is a primitive, and also this is a unit cell. Okay. One special thing about this particular unit cell is that this is nothing but a Voronoi cell. We can divide the. Okay, we'll see about that particular thing. What is a Voronoi cell first of all? Okay, that is something which our professor has already answered. That is, it is a region of the space which is close to a particular lattice point than to any of the other lattice point.
Yeah,
Okay, so this particular region, this entire region which has been drawn over here, we can say that this is closest to this particular lattice point, which is this region is closest to this particular point and not to this particular point and not to any of the point of the lattice one. Okay, and this particular region we call it to be the Voronoi cell. This is a square pattern. That's why we are able to see that the very small, very simple lattice, very simple Voronoi cell. Okay, but it's not like that. It's not always like that. Voronoi cell can be very complicated. Like in the video, also a professor has discussed about the BCC, like the Voronoi cell of the body-centered cubic, and that was a tetrachydecahedron having the 4 phases. Sorry, 14 phases. Okay, we'll discuss about those things also. Okay, so now we got to know that this is a nothing but a unit cell and also a primitive unit cell. What about C? Is it a unit cell?
what look like? If we repeat this,
Let's repeat it. Okay, so we have this particular thing and let's repeat it. Yeah, we are able to do
yeah,
it.
it can. Yeah, yeah.
And now let's repeat both of them together. It is
Mm.
able to fill the space, entire space.
Yes, yes, yes.
So we can say that, yeah, this is a nothing but a primitive unit cell. Sorry, this is
Yeah,
nothing but a
unison.
unit cell.
Yeah.
Now, whether the next question, whether it's primitive or not, that is something which we need to answer. So yeah, can you tell me whether it's primitive or not?
It's a non-primitive.
Yeah, it's a non-primitive. Why? The reason is that
Because
we can
lattice
always we
point
can
is more than one. Like three is in between, and then the edges also we have to.
yeah. So at the corner, effectively, how much of the corner is contributing to our unit cell? So let's try to answer that. How many lattice points are associated with this particular unit cell? Yeah. So how much this and this together is contributing? See, in the when we are talking about the square, we say that okay, this is one by
One
fourth,
by four.
this is one by fourth, and this is one by fourth, and this is one by four,
Yeah.
and that's what they are contributing.
Mm.
Another way of saying that how many angle it is making, it is 90,
Yeah.
90, 90, and 90. Effectively, effectively what is 360?
360 by 4.
Yeah.
Oh, sorry.
And if we
360
add
by
them,
9.
yeah. So if I add all of the angle, I will get 360,
Yeah.
right? And that is nothing, that is contributing 360 degrees contributing to the one lattice point. Okay. What about how many angle this will make? This entire thing, if I add them, this will make
Mm, 360
this
only.
360 only because they are the parallelograms.
Yeah.
Rhombus we can say. like one of the type of the paragram only. So they are going to make 360. That is nothing but it will contribute to the one. So at the edges, the lattice point which is associated with the at the corner, sorry, not that, the lattice point associated with the corner of this particular unit cell will effectively contribute to the one,
Yeah.
and this will be 3.
Four.
How much it will make 4. Okay. So now we got that. Let's go to the this particular our question. So we got to know that our this A was having how many lattice point? We calculated it, right?
Mm,
It was 5.
yeah.
And B we know it
One.
is 1 lattice point. And C we got to know that it
Four.
is nothing but 4.
Four.
If someone let's move, like we have already answered this particular question, fourth one. Now let's try to make it a little bit more complicated. Like if someone tell us to draw, find the volume of this particular unit cells.
Mm,
Okay. So what we can like easily, if I say that this is A and this is also A. Okay. Can you answer me what is the what will be the volume of the B? Let's try to write volume over here. What is the volume of B?
mm, it is A square.
Yeah, it will be A square. Okay. How many? What about the this particular figure A? How many square lattice squares will be filled? It will fill
One,
5.
one, three, four,
So
five.
what? Yeah. So how much will be the volume of it?
Five is square, I guess.
Yeah,
25.
5. Yeah, 5 A square. It will be right.
Yeah.
This will be A square. This will be A square. This A square,
Yeah,
and A
yeah.
square.
So 5A square, sorry.
Lattice square. See, it was having the one lattice point. It was having the 5 lattice
Five
point.
that.
It's sorry, I should write 5 one. Yeah. So its volume got increased by 5 times. Right. What about this? Will we be able to answer this?
4A square.
So how it will be 4A square only without answering anything, without seeing anything, just how many lattice point is associated with this particular unit cell, we can answer that. So for the Voronoi cell also, how many in all the cases we know that how much Voronoi cell consists of?
Five.
Voronoi cell always consists of one lattice point, right?
Yeah.
We all know that it is always consisted of one lattice point. So now whether you draw the Voronoi cell for the BCC, whether you draw it for the FCC, you
Yeah, yeah, yeah. It's a
can easily find its
volume.
volume.
Yes.
Okay. So let's without drawing the BCC, like without drawing the Voronoi cell of the BCC, let's have one BCC. Okay. Okay. So at the center we are having one lattice point, and the entirely we are having the how many lattice points at the edges also. So effective, let us say the length is nothing but a, like all the dimensions of the particular and okay, that these are nothing but a. So all of them are the lengthwise they are a only. How many lattice points are associated with the BCC
Two.
lattice point? Yeah, it will be 2. And what is the volume of this particular BCC then?
2A square.
Not, yeah, no, it won't be 2A square. It will be a times a, right?
Sorry, yeah,
So
yeah,
how
it's volume. Yeah, sorry.
a cube,
Yeah, three. Yeah.
a cube, the
So 2A
overall
cube.
a cube. So
Yeah,
we
yeah.
know for the lattice, for the two lattice point, we are having the a cube. We know in the Wigner-seitz cell or Voronoi cell, we have effectively we are having the one lattice point.
Okay.
So how much its volume will be? If it is a cube, for the two it is a cube. For one lattice point, it will be
Q by 2 means
yeah a
half
cube
A
by
cube.
2, half of it. Right. Perfect. So in this way, we got to know what about the FCC. If the volume of the FCC is having the a cube,
Yeah.
what will be its Voronoi cell volume?
Uh,
Q will be corresponding to the full lattice point, right?
full.
The So one
So,
lattice point, it,
oh yeah, yeah, it's 1/4, AQ by 4, I guess.
yeah, it will be a cube by 4. So even though Voronoi cell, which is having the very complicated geometry, if you try to solve by the geometry, it will be very complicated. Uh, if you try to find the volume of the Voronoi cell by the geometry, if you try to apply the geometry over it, it will be very complicated. But from here, we can see that the volume is associated with the particular lattice point. And so using this, we can easily answer those type of questions. Okay. And this one of the this type of question is already been asked in the assignment. You can give a try to it. Okay. Yeah. Okay. So now let's move ahead. So this was the thing which we are discussing. So we discuss about the how what is the volume of the Voronoi cell can be calculated easily. Okay. So now let's move to the next question. This is the Voronoi cell associated with it. Associated with us. So how do we draw a Voronoi cell? We need to draw the Voronoi cell for this particular lattice. And this lattice is what? This is a this is neither a rectangular, this is not a square lattice. Okay. So this is nothing but a oblique lattice. Okay. So we can call it to be the oblique lattice. So in the case of 2D, in the case of two dimension, we are taking a general general pattern or general net we are taking. Right. So now let's select this particular point. We need to draw a Voronoi cell of this particular structure, this particular net. Let us say we are selecting this particular point. Now next point, first we select the origin. Okay, we are going to find the region of the space which is closest to this particular point and farthest from the all the other lattice point. What is the neighboring lattice point is associated with them? That is this, all of them. These are the neighboring lattice point. What we have to do, what we have to do is we'll join this particular lattice point, neighboring lattice point with each other, and we'll take a perpendicular bisector of it. Okay, we'll take a perpendicular bisector of it somewhere over here. Okay, let's call that, let's say, not 100% it is. You can always buy the compass and protractor. You can select a particular, what we can say is a perpendicular bisector to it. So this is how we can say that this particular region below this particular line, this particular region is closest to this particular our origin lattice point. Okay, and farthest from this particular point. Similarly, we have to do for all of them, right? So let's try to do it. Let's try to find a rough figure. Let's try to make it rough figure. Okay, we are joining these two things, and we are making a perpendicular bisector of it. Okay, let's make a perpendicular bisector to it.
Oh my God, what do
Similarly,
you
we can
say?
go for the another also. See, this is the farthest. These two were the close. Okay, so now let's draw it. Let's draw the perpendicular bisector of this one. Okay. Let me make the perpendicular bisector of a different color. We'll make it of the red color. Now let's similarly we have to associate all the lattice point, neighboring lattice point with each other, and we'll make a perpendicular bisector of them. Let's do for all of it. Similarly, we'll go for this also. This will be parallel to this. Okay, so we can say that it will be something like this. And the perpendicular bisector of this will be parallel to perpendicular bisector of this one. By geometry, we can say that. Okay, so we can draw it over here. Perpendicular bisector of this one, this particular point
उसे 3 आवाज है
1. Perpendicular bisector of the point 1 with the origin will be parallel to the perpendicular bisector of this. two with the origin by symmetry, we can say. Okay, so let's try to move them. Oh, by mistake, I click on the flag. Let's go back. Yeah, something like this. Perfect. So now we draw the perpendicular bisector. On an average, we draw the perpendicular bisector for all of them. Okay. So now we need to find the region of the particular space which is closest to the our origin. We can draw it. We can easily draw it. We'll choose the closest one, which was the inside one over here. And this is nothing but our Voronoi cell of the generalized 2D lattice. Okay, that is a oblique cube 2D lattice. Okay, so in the case of what we can say of for the square case which we have discussed, the Voronoi cell was very simple. It was a square only. But here we can say that the Voronoi cell is very complicated in nature. It is something like something of this sort. Like it's mentioned in the books how it is drawn. Let me tell you. Like this is it will it's something like this for the obliques net, and this is how it is also looking like having the 6 edges. Okay. So now, if we need to find the what is the volume of this particular, what is the area of this particular Voronoi cell of 2D lattice, all I have to give you is the what is a this particular thing and what is the height of this particular. Okay. So if one draw, we know that how much lattice point is associated with this particular Voronoi cell. It is nothing but one,
Hmm.
right? And we can select one particular primitive type primitive unit cell, and we can find its area. We know the area of the parallelogram is nothing but base into height. Okay. So if one
Okay.
is giving you the base and if one is giving the height, all you have to do is b into h, and the same area will be corresponding to this also, like the b into h. The area of this particular complicated figure and the area of this particular simplified primitive unit cell, they both are equal with each other, and simply we can draw it, and simply we can find it. Right? Any doubt in it?
So nearby all the points, we have to join them and draw a perpendicular bisector.
Yeah, we have to just join them and do it to the nearby points.
Okay. And then the area surrounded by nearby that point is the
Yeah,
area near. Huh?
yeah. So area which is near to the line which we have, that is
Near to
a
the line to that particular lattice point, right?
yeah, to that particular. So the reason which is near to that particular lattice point, like there is a two side. This particular bisector is creating the two side. The
Yeah. So
one
which
side
is
is farther.
nearer to that lattice point, we have to consider that one, right?
Yeah, that is the one. Yeah.
Okay. Okay.
So here, yeah. So here we can see that the figure, like I have drawn it using the compass and all. So we can
Okay.
see that how it is looking like. Okay. So I selected this particular 2 point and draw the perpendicular bisector to it. Similar for the other also. Okay. And the region which is like we I not selected this particular region because we know that this particular line is also dividing our figure. Okay. So here this is the closest one, the closest line I have chosen that one, and this region is something which is known as the Wigner-seitz cell for the complicated oblique cell. Sort of complicated, but no, it's not. Like just the geometry of it, we can easily do this particular part, right? So if it is for the rectangle, if it is for the square, you can easily do it. Okay, yeah. And also we can easily find the area or volume associated with this particular lattice point or particular Voronoi cell. Okay. So any doubt in this till now?
No, go ahead.
This was the thing. Yeah. This is the lattice point which we discussed. Like this was the net, the entire net of which we have drawn the Voronoi cell. Just bisector of it and it's easy. So now, what about if someone try to find its volume, sorry, its area by the geometry, how complicated it will be? You have to find the area of this entire rectangle to this particular point, and we have to separate this particular area. And it will require a lot of calculation, lot of geometry and all. Okay, but instead of doing that, instead of finding by the geometry, you should do by the effective the area associated with the particular lattice point. Okay, okay. So now let's move ahead and go to the next particular question. Okay, so this is a question number 6. Yeah, and then we have one more question. Okay, so now what is the question is that determine the indices or the direction shown in the accompanying figure. So this is a figure which is available to us. What we need to do, we need to find the indices, Miller indices associated with this particular direction. Okay, so yeah, can you tell me like what is the procedure to find the direction, to find the Miller indices of a direction?
First, we
The
have to
first thing
find
is,
out the coordinates.
yeah. So in order to find out
Yeah.
the coordinate, what we need to do first, we will associate it with the associate origin with it. Okay. And in the case of directions, we associate this particular origin with the tail of the particular direction. So we can say that we are considering this to be the 0, 0, 0, the tail to be the origin. After that, and yeah, just as you say that we have to find the crystallographic coordinate system. Crystallographic coordinate, the axis associated with the crystallographic coordinate system. So this is our crystallographic coordinate system, that is in this direction it is a vector. This will be in the y direction, this is a b vector, and we can see in this direction this is c vector. X, Y, Z, one shouldn't specify. You can ignore that part, like there is no X, there is no Y, there is no Z. This can be 90, this cannot be 90, it can be anything. The beauty of the coordinate system, crystallographic coordinate system, is that we can find the direction. We can find the mirror indices of a direction without knowing what is the angle between them. What is the angle between the coordinate axis? Okay, it can be triclinic, it can be monoclinic and all. Okay, so for the timing, we can ignore this X, Y, and Z part. And this is something which we have done. Now what we need to do next step is to find the how much distance it is traveling in the particular direction, in A direction, in B direction, and in C direction, and by what amount. So in A direction, in this x-axis, how much it is traveling, and in B, how much it is traveling, and in C. That is, we have to go from tail to the head. This is our aim, and we need to go by the this particular coordinate system. Okay. So starting from this particular origin, in the A direction, we have to go by the minus of A. That is in negative. If I'm choosing this particular origin, this will be my C axis, this will be my B axis, and this is my A axis, right? So in the A direction, I'm going by the amount of A, and from here, then I will go to this particular direction, and then I will go to this particular direction. So our path is something like this, something of this sort, right? So from here, I'm going A by the negative, sorry, -1. In the B direction, by how much amount I'm going? I'm going by this
Half
particular
1/2.
one only, right? In B direction, we are going by the, yeah, sorry.
Half
So this was the C direction,
C
and
direction.
this is a
Yes.
B. So in B direction, we are going by the 1/2. Perfect. And in the C direction, we are going by
What? One.
1, right? We are going all the way up. So what is the Miller indices? We can write like 1 bar for the in order to write the Miller indices, we will ignore this particular lattice, this particular crystallographic coordinate. Okay, A, B, and C. So what we write, 1 bar, 1 by 2, and 1. What we can do, let's see, -1, I write to be the 1 bar. In order for us to write the Miller indices, we have to ignore the, we have to eliminate the fractions. Okay. In order to do that, we will multiply entire thing by the 2. So it will be 2 bar. It will be 1. It will be 2. Is it right?
Yeah.
So is this entirely my Miller indices or anything left is there for us to do?
We have
We
to
need to
put
write
a
the
bracket, the square bracket.
square bracket. Okay. So we put the square bracket, and this is our entirely the Miller indices of a particular direction. Right. Square bracket we put for the direction. If we're talking about the family of direction, then what we will put?
Mm,
We'll put this type of bracket for the
Paren parenthesis?
Parenthesis, no, no, no. What is
Not parenthesis. Uh, we,
yeah. For the plane, we'll use this particular family of plane.
mm,
Even though plane is not been discussed here,
mm,
we can still write. This will be the for the plane. This will be for the single plane. Okay. Note that there is no comma associated. We are not associating any comma. Okay. So if it is there, just remove it. Okay. This is how we write the. This is how we write the Miller indices of of the particular directions. Okay. So now let's move to the next question. Next question is telling us the we have to find the yeah, sorry, we have to sketch the direction. Okay. So direction this time Miller indices has been given to us, and we need to go to the we need to draw the direction of it. That is the reverse of the previous question which we did. Okay. Let's start with the 101, the first one. So here it is. So let's go with let me make one more duplicate so that we can solve all 4 questions in the different cells. So we'll go with the reverse direction. Okay. So 10101. We'll write this in terms of A, B, and C. The first is associated with the A, 1, 0, and then again 1. We'll write a plus sign with that. That is, it's a translation we are doing. So what we are seeing is that we are going in the A direction by 1. We are going in the C direction by 1. And origin and in B direction, we are not going anywhere. All of them are positive. Okay. So let's select our origin at the center only. So let us say this is my center. This is my origin for a time being. This particular origin, not what we have to do in the A direction, we have to go by 1 unit by this. In the B direction, we don't have to go anywhere. Like this is a B direction. Okay. This is the A direction. And this is the C direction. In the B direction, we don't have to go anywhere. So B is done. And in the C direction, we are still at this particular point only. Now we have to go in the C direction by the amount of 1. That is over here. So we started with the origin. So our tail of the vector, tail of the direction will lie on this particular thing. And our head will lie on this particular point. Okay, so let's move it. So this is how. This is the my Miller direction. This is the direction of the particular Miller indices that is given to us. Okay, so first part is clear. Now let's move to the second one. Yeah. That is 2 1 1. Can we draw over here also only? Yeah. So here we are having the 2 1 1. Okay. So let's write the Miller indices in terms of the A, B, and C. Okay. So A, B, and C has been given to us. Yes, sir, you can put it over here. So A, B, and C has been given to us. That is the crystallographic coordinates. And then we are having the 2 times of A, 1 times of B, and 1 times of C. Okay, this is 2 1 1. All of them are positive. Okay, so here what we have to do is see, this is 1 1, but this is 2. If maximum in this particular unit cell, what we can go for the till only 1 1 and 1 only, right? All the indices, all the by only unit amount I can go in particular direction, but here it is 2. So in order for us to draw this particular directions, either we can extend our unit cell and make it by the twice of the size, like we can just duplicate this and reciprocate, or what we can do, we can divide this particular indices by the 2. Okay, let's divide it and we'll try to draw within this particular direction, within this particular unit cell only. So here we can write A plus 1 by 2 B plus 1 by 2 C. So now what we can see that in the A direction we have to go by unit amount by 1. In B direction we have to go by 1 by 2, and in the C direction we have to go by, again we have to go by 1 by 2. So this was our origin. Since all of them are positive, I will again consider this same thing to be the origin, and I am going by the unit amount in the A direction, and this is how I will land over this particular point. This particular translation is over. Now in the B direction we have to go by the amount of 1 by 2. Let's go. So somewhere over here it will be, and in the C direction we have to go by 1 by 2. So somewhere over again, that is a face of this particular, the face of this particular square, the, the front face of the cube. Okay, so from origin to over here, this is nothing but 2 1 1, right? Is it correct?
Yes. Yes. We got
Yeah.
it.
There was another way for us to do that, like without dividing it. That was nothing but we have to go by 2. Like we will follow this particular for a time being, let us say. So from here, let's select the another color, uh, black will do. Yeah. Considering this to be the origin, will go by the amount of 2A and we'll land over here. And then we will go by the amount of 1 of B. In the B direction, we'll go by the 1. We will land over here in this case. And then there is a 1 times of C, and we'll land over here by going in the C direction. If you join these two things, if you draw it properly, like I not draw it properly, it will be at the in the same direction it will lie. All the difference is that the magnitude of this particular thing, this particular vector is twice of this particular original vector. Since both of them are representing the direction, since we are worried only about the direction, so no need to worry about no need to take a concern of the magnitude. So both the cases, like drawing within the 1 unit cell or drawing within the 2 unit cell, extending the unit cell, both are the fine. Okay, both will do it. Now let's go to the third question. That is a 1 0 2 bar. Since negative is associated with the one of the direction, what we need to do? Okay, let's write A, B, and C. With the A, that we are having 1, then we have 0 with the B, and minus of 2. 2 bar, there is nothing but minus of 2 with the C. Okay, so one thing is that the one freedom is which is associated with us is that we can change the origin. Okay, if I have to draw the minus of C in this particular same unit cell, okay, considering this to be the origin, or I need to do, I need to go in the negative direction of C. Sorry, It's not in that direction. Yeah. Need to go in the this direction by the twice of amount. I don't want to draw that, and I don't want to be in the. I don't want to extend my unit cell. I want to represent my direction within this particular unit cell only. In that case, what I need to do, we can shift the origin in the particular direction which is negative. Okay. So since our C was negative, our C direction, that is along C direction which is negative, the indices associated with the C direction is negative, we'll move our origin to the up in the C direction. And now this is my origin. Okay. But what is the restriction is that one thing is that origin I can shift, but I cannot change the crystallographic chord crystallographic axis. Right? So axis associated with the particular crystallographic coordinate system, I cannot change. So this is again my C direction. This is my B direction, and this is my A direction. Okay. So now what we can do is that considering this to be the origin, we can apply all the things. Again, one more thing is that there is a 2 associated with it. Now we can again the last question which we discussed, that we can extend the unit cell also. We can draw within the same unit cell. So let's restrict ourselves that we will only draw within one unit cell. Okay. So what we will do, we will divide by 1 by 2 to all of them. Okay. So what we can see here, from the origin, I have to go by the amount of 1 by 2 in the A direction. Let's go it. Let's do this. In the A direction, we are going by 1 by 2 amount. In the B direction, that is along this, we are not going by any amount. It is 0. And in the C direction, we are going by the unit amount in the negative direction, in the negative sense. So from here, we are going all the way to the bottom over here, right? So this is our head. This will be the head of our Miller. This is the head of our direction, which is represented by this particular Miller indices. So let's draw it. So considering this to be the origin, we are drawing our direction, and that is how we have done it. Okay. So till now, all we did, we divided the particular axis in the two parts. Okay, there was a 2 associated with it. There is again 2 associated with it. We discussed that how we can shift the origin, and under what condition we have to divide the particular indices. Okay, and whether you want to divide and whether you don't want to divide, it's all up to you. Okay, so now let's move to the final one, that is 3 1 bar 3. So here it is. So this time it is a 3. Again, we'll follow the same procedure. A, B, and C we are having. 3 is associated with the A, that is also plus, and 1 is associated with the B in negative one, negative sense. And with C, there is a 3 again associated. Okay, so now the next question is that where should I take my origin? Should I take it over here? So can anyone tell me, like, where should I take my origin? Or in which direction should I shift? Here B is negative, right?
B direction.
Yeah, in the B direction we will
Then
shift. We'll
A is written that place. Means that age, yeah.
yeah, this one, this edge particular.
Yes, yes,
Yeah,
yes.
yeah. So A, B, C, D. So we'll shift our origin to D. So this will be our next origin. So now considering this particular origin, what we need to do, we are having the 3, -1, and 3 to be the Miller indices. We can extend our unit cell by the 3 times because we are having the 3, but we don't want to do that. We'll divide we'll divide this entire indices by the 3. So we'll get A, we'll get 1 by 3 of B with negative, plus we will get C. Okay. So now let's start with this particular point, and yeah, starting with this particular origin, in the A direction we have to go by the unit amount. That is, we'll go all the way and we'll come over here. Our translation is not over yet. This was just a tail. This is a tail of the our direction. If we are at the C, now, sorry, we are at this particular point. A is over. Now we have to move in the B direction. B direction by the amount of minus of 1 by 3. So where is the B direction? B direction is nothing but this direction, right? This direction is the B direction. In the negative sense, we have to move by 1 by 3. Let's divide this particular thing, this particular length in 3 parts. Okay, so we'll move by somewhere over here. Okay, 1 by 3 in the negative sense. In the C direction, we have to move by the amount of 1. So from here, in the C direction, that is along the upward direction, we'll move by the amount of 1. So from here, we'll go all the way to over here, right? So this will be the head. This is the head of our vector. Now all we need to do, we can join them, head and tail, and this is the direction is being given. And this was the entire questions that we need to discuss. Okay, so now let's make few more questions. Let us say we'll take this particular unit cell, and this time let me mark one direction. And the direction is going something like from here, it is going to the mid of this. Okay, our task is to find what will be its Miller indices. Yeah, so can we do it? Is it possible? Is it doable? What is the step one is that we have to choose the origin, right? So can anyone solve this, and what is the answer? Like I will also solve with you, so we can do it right together. Yeah. So what we can see is that from here, this we will choose the origin over here on the tail of the direction. So this is our origin,
Hmm.
and in the A direction, what we have to move, we have to get to this particular point. So let's move it.
One,
Let's move from here. We are going over this direction, and then we go.
one, 1/2. We can have two paths, right? First, we can go in the negative direction.
1/2.
Yeah. No, there is a negative direction is also associated with it. So this is B, this is A, let us say, and this is, along this it is a C direction. Okay,
No,
crystallographic
I'm
coordinates.
telling first going in direction of A, we can go in direction of B. There can be
Okay,
two
yeah,
paths.
yeah, yeah. There is a two path, so we can
Yes.
go by this amount, this
Yes.
also,
Mm.
this, then this, and
Yeah.
then this.
Hmm.
So
Yeah.
by both the cases,
We
will
should
we
have
get the different or will
no,
we
no,
get the same
same thing we should
Same.
actually.
thing only we will get? So what we are going to get in the A is 1 if we follow the blue one, and in the B direction we will get again how much we will get? We'll
One.
get 1
1/2.
or we'll get -1. We'll get minus of it, right?
-1. Yeah.
And in C
I
direction we'll
think
get
there
1 by
can
2.
be more than two paths, right? But we should have the
One.
same indices.
1/2.
If we take in the C direction first,
Uh, sorry, I not got it.
if we move the first edge in the C direction
Okay,
up to 1, then in the B direction, then once again in A direction, then negative C direction.
okay. So we are moving by this, then we are moving by this.
Then
Is it like that?
yes,
Then
then A direction, then once again in positive C direction, negative C direction.
then this. Okay, let's try to do this also. This is quite interesting. Okay, we'll move it. We'll move by this. So there are multiple paths are there available to us. So let's finish the first one, this blue one which we were trying to do. So 1 -1 and 1 by 2 we are having. Okay,
सारे direction से तो
so
एक ही
we
आना
can say
चाहिए.
that the 1 -1 and 1 by 2 our direction, but we'll not consider this fraction to be our in the Miller indices. Then we'll multiply entire thing by 2. So we can say 2, 2 bar and 1. This is our the Miller indices of the particular direction by the following the blue path. I should have write this also in blue. So now let's go with the red one. That is why we're following this particular path. Okay. So in this direction, which we are moving in C direction by 1. So 1 of C. Okay. Then we move in the negative of A direction. So minus of A. Then we are moving in the positive of, sorry, we are moving in the negative of B direction, right? Over here. So this was the
Yes.
negative of B direction.
Yes.
Then we are moving in the A direction by 1,
Mm.
plus of A. And then after
Minus
that
of
we are
1 by
moving
2 C.
yeah. So we are moving in the minus of 1 upon 2 C. So this will be effectively, it will be the in the C we will be having minus of 1 by 2, sorry, plus of 1 by 2 C. In the B we'll be having minus of 1, and in the A we will be having A, that is plus 1.
Yes.
And
Because it is vector addition, so
yeah,
from
it will be
where we
cancelled.
start and from where we end, that matters. In the path,
Yeah,
it is.
it doesn't matter. Yeah, same will go with this particular path also. Let us say, for example, green one. If I
Mm.
go by this particular path also,
Mm.
I will get the same thing.
Same thing. Mm. Yeah. Yes.
Okay. So here there won't be any conflict, like all are equal, and here also we can say that they are cancel out with each other overall. Effectively, C will be cancel out with each other one by, like, some extent we can mathematically subtract them, and
Mm.
again we can get back to the same part, and again we can write the, yeah, this will be our Miller indices. And if let us say we are doing some mathematically, like if we are finding a Miller indices and we are getting the opposite of it, 2 2 bar 2 and 1 bar. Here we can say that, okay, yeah, this will also be, this will also will do. This is also fine with us. Okay, just the opposite negative of it won't affect us. So the direction, the Miller indices of the same thing, this both are the same somewhat. Okay, yeah. So this was the entire thing which we have discussed from starting to the end. Okay, so we first discuss about the what are the syllabus that has been covered in the our, that has been covered in the particular week, this week one. Okay. Then after that, we discuss about the few questions by the this art, which is by the MC Escher, and we saw that there are the lattice point associated with the each features, which is movable, like the same lattice point I can move and I can make it over here. Okay, and we see discussed that we can associate a unit cell with them, and we can find the, okay, this is the unit cell, and if I repeat this particular unit cell, I will get the entire pattern. Same goes true for this also. Okay, we have selected the particular lattice points, the point associated with the features. See, in all of them, we are selecting the tip of the face to be the lattice point. Okay, one can also select the tail, but if you are doing some one thing, just follow it. Okay, and then what we can say that this is the entire thing which we are having. If I move it over here, let us say I'm selecting the tail of the feature, I will get from this particular point, which was initially over here. So this particular point has been moved, this particular point. And the same goes for other point also, like they all are symmetrically equivalent. So this art by the MCS is very popular in the crystallography. Okay. We discuss about the what is a primitive basis and what is a non-primitive basis, what is a primitive unit cell and what is a not primitive unit cell. We discuss how to find the volume, sorry, how to find the area associated with them. We can also find the volume associated with them. We discuss about the Voronoi cell also, and we discuss that how we can draw the, how we can find the area of the Voronoi cell, how we can draw them. Okay, in the, this is the most general case in the 2D net. In the 3D it will be even more complicated in nature. Okay, but still here we are dividing by the lines. In 2D we will sorry, in 3D we will divide it by the plane, and the area enclosed, so the volume enclosed by the particular intersection of the planes, those will be our Voronoi cell. Okay, we see that how effectively, how easily we can find the area or volume associated with the Voronoi cell. Voronoi cell also known as the Wigner-seitz cell,
Mhm.
okay, or Dirichlet cell. Then we discuss about the directions of the lattice, direction of the Miller indices direction associated with them. Okay, and how we can, these questions are taken from the Callister. Okay, these are the few good questions as in that particular book. Okay, and that's what's all from my side. Okay, so any question before we end this particular session, I would like to discuss if there is any from the particular this particular syllabus that has been covered.
Everything is fine now.
Okay.
So,
Yeah, so we have covered all of the things, and the recording of this will be available on the site and also will be provided to you by the link. Okay. So yeah, that was all from my side.